Go.
So did you get, I got 416 to negative 16. Yeah. Did you get 4 times 16 to negative 16? Yeah, that's what I got there.
Well, -2 doesn't, it's not in the right.
Wait,
Nice.
get him and do it. Just do it. No, that's question.
4 and 2.
Go.
Johnson gets the famous
You know you're not supposed to zoom in. Just get your phone. Minus the grass.
And then you open a PDF in a browser and then save it. It doesn't save. You know how many times it's destroyed me? Over and over and over and over and over again. If someone sends you a PDF that you need to fill out, and then you just click on it, and then it opens up in your browser, or at least Chrome does this, then you just put in like 20 minutes of work into filling out the PDF, and then you just save, it just doesn't work. It's like a defect, it's like this, probably the stupidest thing
That's why you always have to update
in the world of computers. And I just spent 20 minutes filling out the form, and now I just have to do it all over again. Except this time I'm going to do it in 1 minute.
I would love to
Don't tell them what to do. That's not science, that's the first put arrow.
wow.
What causes a late?
Like blueberries. Lakes, just like
When the depression.
yeah, just a depression where if a stream feeds into it, it doesn't drown it.
Okay, good. Can you like fold it up, put it in the envelope, make it seem like okay? Good, thanks. All right. So what happened? Oh yeah, this was an easy one. You basically just do it, right? Here's a function. Take the derivative, factor it. It's beautiful. Oh, this is the problem where you actually had to do stuff now, right? They said find the minimum and maximum on the interval 0, 4. So when you plug in 0, you get 0. When you plug in 4, you get 64 minus 48 is 16. So now you check you take the derivative, you look for the critical values, and the only critical value on this interval is 2. You plug in 2, and you get negative 16. So the min is negative 16, the max is 16. Okay, how do we feel about this?
Great.
Good. Can I have this homework? Let's put it right over there. Yeah.
Bring it by the homework.
Shared.
And water. Waterboard, like, carrot stuff, like waterboard.
All right, guys, bold theorem coming today. Are you ready for it? Sheep? Stylish? All of those things and more. Kiara, can you raise the board back there when you get a chance? All right. So, yeah. I think I'm just going to. Maybe I'll start with something cool. So, starting with something cool. Here is a gorilla. Monkey. Gorilla. It's a primate. We don't have time to have these kind of conversations. Just focus on the stuffed animal. All right. But it's just a monkey, right? Gorillas don't have tails. Is that what you're trying to say? Yeah, it's a monkey. Okay, here's a monkey. I am going to throw the monkey up into the air, and I'm going to catch
Or no animals.
it. So please focus on the height of the monkey. And I'm going to try to release it from this same height. So ready? So wait, what are you going to do? No, don't try to do any fancy camera work. Here goes the monkey. Up, and I just caught it. All right, someone tell me what happened. Yeah,
He moved the paramount.
went up in the air.
Velocity.
Oh, interesting. All right, good. He said you threw the monkey up in the air, then it stopped for a moment and came back down. Please use fancy calculus language.
Derivative becomes
Derivative of the integration of
What?
DH.
The derivative of the.
Now focus on the height of the monkey as a function of time. Well, what was the rate at which the height was changing? And Didi said he already said it. Didi, say it again.
0.
0. What was 0?
The rate of change of the height.
Yeah, it seems to that to be the case, right? So what's happening to the velocity of the monkey? Well, as I throw it up in the air, it's getting higher, 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 higher. At this point, the derivative is positive because the height is increasing. The height number is getting bigger. The rate of change is positive. And then there's this exact moment when the monkey is all the way up the top that it pauses for like a second and its height is not changing for a moment. And then he falls back down again and I just catch him like this. Okay. All right. So there's a theorem. It is called Rolle's theorem. Due to some French guy, undoubtedly, named Rolle. And basically, Rolle's theorem says what goes up must come down. What goes up must come down. Yoni, specifically, assuming the following conditions have actually. So first of all, is that true that what goes up must come down?
No. Assuming
No, it's
Okay.
not.
Actually, okay. All right. So let's drop. There's so many cool ways to do this lesson, and then there's just like one boring way. I think I'm just gonna do the boring way.
No. Come on, Mr.
Alright, so suppose let's try to do this. So here's the function, and what's crucial is that I catch the monkey at the same place that I release it from. So that's another way of saying that I have some kind of closed interval, and on that closed interval, the y values are the same at the left and right endpoint of the interval. So if the y values are the same at the left and right endpoints of the interval, can I say that somewhere the derivative is 0? What goes up must come down, right?
What if it's a point? What if it's like a then it wouldn't have a derivative?
What if it's like absolute value
Yeah.
or negative absolute value?
Yeah, what if it's like negative absolute value they're saying? What if the monkey got thrown up and then like hit like a
Person.
ceiling and then just kind of like jump back, or like maybe that would be like a that would have to be like a bouncy ceiling for that to happen, right? Is the derivative ever 0 there? Ignore the physics for a moment, just look at the graph. No. What's another situation that could happen? What if there was some monkey portation that happened, right? What if the monkey just suddenly disappeared and then just like reappeared like over here? Yeah, 2001 a monkey. That's not even funny. Okay, this was a lame attempt to kind of introduce some things which I feel we should be forced to mention before we can state the what goes up must come down theorem. What Brittany, tell me some things that have to be true in order for Aditi Shetty's comment that somewhere the derivative is 0. What do I have to ensure first?
That it's continuous.
That it's continuous and
That y.
someone else?
It has critical.
Alianwar?
It has to be differentiable.
Yeah, he says he's also just looking at the book, cheater.
Yeah.
Yeah. Also, we can't have that sharp point thing yet. Okay, so here it is. this is Rolle's theorem. Here's what it says. It says if f is continuous on the closed interval AB, so I have a continuous function, and f is differentiable on the open interval AB. In other words, no monkey portation, no weird, strange physics in which the monkeys, right? You have a continuous function and a differentiable function. And the crucial other fact is that we start and end at the same place. So if f of A equals f of B, if all three of these things hold, then, as you guys mentioned, there must be somewhere on that interval in which the derivative is 0. There exists a C on the interval AB such that f prime of C is 0. This is Rolle's theorem. Let's make some pictures. What are all the kinds of possible things that can sort of happen? If you tell me that these, let's just draw some functions that satisfy Rolle's theorem. What's one thing that could happen? If you give me, Aliana, close the book. Open your mind. Yeah, close the book. Nikili, what's one thing that could happen? If f of A equals f of B, it's continuous and differentiable. By telling me that the function is continuous and differentiable, you impose a pretty strong constraint on the kinds of things this function could look like. What's the most boring thing that could happen on this interval? Could just be a totally constant function. By the way, if it's totally constant, is there a place where the derivative is 0? Yeah, in fact, it's 0 everywhere. Okay, what's another thing that might happen?
An upside down parabola.
Yeah, it could just do could be like a monkey. We could go up and then back down again, upside down parabola. That's something that could happen. Do we feel that somewhere in there the derivative is going to be 0? Yeah, I feel that. What's a different thing that could happen? Now this is like monkey reverse gravity. Yeah, bungee jump. Yeah, it could just kind of go like that, right? But again, if it goes down, it has to come back up. That's the law of bungee jumping. Or, like, what else? What else might happen?
It could go like up and down.
Yeah, how about just like anything else, right? It could just go up and down, who knows, like, some number of times. And this thing where it says there exists, this is like a math there exists, right? It doesn't say there's exactly one, it's just when we say there is one, we just mean there's at least one. Okay, in all of these cases, I somehow feel that that this theorem is true. All right, let's prove it. This proof naturally breaks down into cases. So let's do case 1 first. Well, case 1 is this case, in which the function is just constant. This seems kind of easy. So suppose case 1 says, write this all out? Yeah, I guess I'll write this all out. So case 1 is f of x is constant. Is constant on the interval AB. So supposing the function has no change. Well, if the function is constant, then f of x just equals k. Well, my goal is to show that somewhere the derivative is 0. So take the derivative of this. So the derivative of a constant function just is 0. So we're just done, right? Yeah. So let C be any point in the interval AB. Then f prime of C is 0. Alright. So I've succeeded in showing that somewhere the derivative is 0 if the function is constant. Okay, that was just like the trivial, boring case. Now let's look at case 2. All right, case 2. Well, I don't know. You tell me. What are the sort of ways in which I might break it down into cases? Either the function's constant everywhere.
It has
Polynomial that contains A and B.
Well, I don't want to get in. I don't want to. This is a really like basic kind of theorem. I don't want it to apply just to polynomial. It's going to apply to. It's going to apply to really any continuous function at all.
Something with extreme.
Something with extrema, she says. Yeah. Okay. Well, yeah. So it's either. I mean, there are basically only three possible things that can happen. It can be constant, or I guess there are only two possible things, like constant or not. Okay. So constant or not. If it's not constant, then it means, it means that somewhere it's going to be either above or below that y value. So case 2, let's just suppose that somewhere it's above that y value. So case 2 says f of x is greater than f of a. F of x is greater than f of a somewhere on the interval ab. This is pretty vague. I'm just saying that this is a function which somewhere on that interval is larger than it is at the left and right endpoint. Yes. Okay. You're gonna. All right. Great. All right. Anyone? So what? So this is like my case 1. This is like my case 2. Somewhere the function is larger. Somewhere I am above the line. Tell me why in your own words. Why do you think? Why do you think the derivative? Let's just talk it out. Why do you think there's a point where the derivative is 0 in this case? Because it goes up and it has to come back down. Okay, keep talking. Someone else.
The derivative starts out positive and then it eventually becomes negative, and since
She thinks the derivative starts out positive, eventually goes negative. Yeah, but okay, I don't maybe necessarily know that. Yeah.
Intermediate value theorem.
Intermediate value. He's throwing out terms. It's a good idea. I don't know if that's relevant at all.
You got a point below the x-axis and a point above the x-axis if you plot the derivative of this, and so there has to be. And since it's continuous, there has to be
But I don't know anything about the derivative being positive and then negative. Actually, I don't know that. It looks like that on my picture. I really only know like one thing. I know it's continuous. I know it's differentiable. I know I start and end at the same place. And I know that somewhere I'm to be found up here. Yeah.
There's like a local maximum.
He says local max. Why is there a local max?
Because in that interval there's
Yeah, why? But how do I know that there's a local max at all?
f of c is greater than, like there's some interval for which f of c is greater than like f of all the x or something.
Okay, this is kind of hard because I'm asking you guys to be like real mathematicians and just like make total use of all the theorems that have been previously discussed and named in this class. For starters, why must there be any max at all? That's also relevant. Oh man. Alright. Yeah, guys, we proved, what was the big theorem last class that we discussed that was like actually the title of the entire class, which we didn't prove because it's too hard, but we made a big deal about. The extreme value theorem. What does the extreme value theorem say?
If f is continuous on the closed interval ab, then f has a max and min on.
Yeah, so for starters, this function must have a max because this function is continuous. So by the extreme value theorem, since f is continuous on the closed interval AB, the extreme value theorem tells me that f has a maximum. Okay, that's probably worth mentioning, right? Somewhere on that interval, the function is largest. All right. What are all the possible kinds of maximums that we can have? Hint, there are only two possibilities for a maximum. Where do I have to look for the maximum?
Endpoints and
Endpoints and, Brittany?
critical.
Okay, yeah, that's true, but even more, forget about like how to find them, just like where are the two possible kind of maxes? It's either endpoints or a relative max. I mean, those are the only options, right? If I have a maximum, the maximum must occur either at the endpoints or at a relative max. Well, which is it in this case?
Relative max because the endpoints are.
No, it's not because they're equal, that's
It's
irrelevant.
because it says f of x is greater than.
Yeah, no, in case 2, I guess it's pretty hard. Maybe I should just do the proof and just instead of asking you guys weird questions. The function is bigger than f of a somewhere, right? So since the whole nature of case 2 is that f of a cannot possibly be the max, because I'm assuming that somewhere the function is larger than f of a. So by the extreme value theorem, it must have a max, and since f of x is bigger than f of a somewhere, the endpoint cannot be the max, right? F of a cannot be the max, cannot be the max, so what can I conclude? There must be a relative max. So there must be a relative max at x equals c. So if there must be a relative max at x equals c, then what can I say about that relative max? Now, somebody. Okay, too slow. There's a relative max. What's my goal? What am I trying to do? Ugh. Then the derivative is 0. Why? Yeah, because of Fermat's theorem, right? That's precisely what Fermat's theorem tells me, right? It tells me that if I have a relative max and the function is differentiable, then the derivative must be 0. So since f is differentiable on the interval a, b, then f prime of c exists. And now we have Fermat's theorem. Fermat's theorem says that if the derivative exists and the derivative is 0, or no, if the derivative exists and there's a relative max, then the derivative must be 0. So by Fermat's theorem, since f of c is a relative max and f prime of c exists, f prime of c has to be 0. So basically what we do is we use the extreme value theorem to say that there must be a max. The max can't be the endpoints, so it must be a relative max. And by Fermat's theorem, which we proved last class, then the derivative must be 0 there. I guess that's just very theoretical. All right, case 3. What's case 3? What's up? Yes, f of x is less than f of a somewhere on the interval a, b. Okay, so now we're here in case 3. Okay, so let's just talk it out. Elijah, just talk it out. We don't have time to write it all. Just like say everything. Come on, man.
Can someone else say stuff?
Okay, how about me? So again, we just go through the exact same logic. By the extreme value theorem, since the function's continuous on a closed interval, there must be a minimum. Since there must be a minimum, but by assumption the derivative is less than f of a somewhere on that interval, then the minimum cannot be the endpoints. And since the minimum cannot be the endpoints, the minimum must occur at a relative minimum. Thus, I have shown that there must be a relative minimum. But since the function is differentiable, the derivative exists everywhere, and thus, by Fermat's theorem again, if there's a relative minimum and the derivative exists, then the derivative must be 0, so I've proved there's another point where it's 0. Right? And if it's above and below, then there are just simply going to be 2 different points. So there's like C1, C2, or whatever. Okay. Rolle's theorem is kind of awesome. It is a very sort of theoretical theorem. It enables you to mostly to just like prove other theorems. But there are some things that you can do with it. So here's an application. So this is just an application of Rolle's theorem. All right. Use calculus to prove that x cubed plus x minus 1 equals 0 has exactly one real root. Prove that this equation has exactly one solution. All right, we need to go fast. Will, say something. Lathrop, say something.
We should use Rolle's theorem.
What does it mean to, yeah, that's true. What does it mean to prove that an equation has exactly one real root? Logically speaking, that's really like two separate statements kind of combined into one.
Show that its derivative is 0 when the y equals 0.
No, you guys need to get better at math. Be better at math. What does exactly one mean?
It only changes.
No, just logically, like down to like the bare bones of like logical meaning. What does it mean when someone says I have exactly one lollipop? What do they really say?
It only has one.
Thank you. It's really like two statements in one, right? Saying that there's exactly one is really like saying there is one, and also there aren't two. Exactly. Saying you have exactly one lollipop is really like a combination of saying I have a lollipop and I don't have two lollipops. Okay, so go. Prove those separately. First prove that this function, first prove that this equation has a solution, and then prove that it doesn't have two solutions. You see what I'm talking about? This is like the math way to do this. Anytime someone says prove that there's exactly one of something, this is what you do. Okay, I take it back. We just have no time to do this problem. I'm sorry. It's really fun if I give you guys like 10 minutes to think it out. No time. Brittany, let's just do it. Here's the function. f of x equals x cubed plus x minus 1. Tell me about this function. It's a polynomial, thus it's continuous and differentiable everywhere. Why does this function have a root?
Because there's an x value that when you plug it in, f of x is 0.
What?
Because there is an x value that when you plug it in, f
Why?
of x is 0.
Why? Why? Did he show you?
Can't you just use the intermediate value
Yeah,
theorem?
start,
It's
go.
Negative, it's negative at like -1 and it's positive at like 3 and then you know that somewhere.
Exactly. Plug in like 0, for example. If you plug in 0, what do you get?
-1.
-1, bam. Plug in 1, what do you get?
1.
1. No. Yes. If you plug in 0, you get -1. If you plug in 1, you get 1. Thus, the picture of this function kind of looks like this. And now, it must cross. Why?
Intermediate value.
Intermediate value theorem. So this is a sort of like a review of that kind of thing, right? We say that f is a polynomial, so continuous and differentiable everywhere. So continuous and differentiable certainly on the interval, on the closed interval 0, 1. And 0 is a y value which is between f of 1, which is 1, and f of 0, which is -1. You guys remember all this kind of stuff, Garrett? I'm picking a y value which is between f of 0 and f of 1. Actually, the fact that it's differentiable is irrelevant at the moment. I shouldn't have written that. It's a polynomial, so it's continuous on the interval 0, 1. The intermediate value theorem only requires continuity. If it's a continuous function, this is a continuous function, it's continuous on this interval. There's this y value which is between 0 and 1. So by the intermediate value theorem, there exists a c on the interval 0, 1 such that f of c is 0. Okay, congratulations. We just proved that this function has a root. So step 1 complete. What's step 2 in proving that this function is exactly one root?
That it doesn't have one.
That it cannot have two roots. Okay, how can we prove that this function cannot have two roots? Hit.
Rolls theorem.
Okay, you're just saying that. How can we prove, if someone says prove that something cannot happen, what do you do?
Try to
do
prove
it.
that it doesn't happen.
Assume that it does, yeah. So what we're going to do now is we're going to assume that f has two roots, a and b.
X minus a times x minus
So
a.
no. It's sort of like it's a sort of irrelevant that this is upon. Well, so it has two roots, a and b. So what I know is that f of a equals 0 and f of b equals 0. And what we're going to try to do is we're going to try to show that this is impossible, right? Why is this impossible? Okay, f of a equals 0 and f of b equals 0. You heard anything about that?
Oh, so
Yeah.
Rolle's theorem.
Apply Rolle's theorem. Yeah, of course, right? I mean, what we have is the following picture. Here's a, and here's b. Here's 0, and this is also 0. So this is exactly what we're going to do. We're going to apply Rolle's theorem. Are the conditions of Rolle's theorem met? Is it continuous on the interval AB?
Yes.
Is it differentiable on the interval AB?
Yeah.
Yeah, of course, it's a polynomial. It's continuous and differentiable everywhere. And f of a equals f of b. Oh, b should probably be here at 0. Sorry. Alright, so what's the problem? What does Rolle's theorem say?
There's a place where the derivative is 0.
There exists a point A on the interval AB such that
At the time of c is 0.
okay. So
Now we derive.
take the derivative. What is the derivative of this
That's
function?
3x squared plus 1. 3x squared plus 1.
And that can never equal 0.
Ta-da. If this function is x cubed plus x minus 1, its derivative just happens to be 3x squared plus 1. But that 3x squared plus 1 expression is always greater than 0. So on the one hand, this derivative is always positive. But if we assume that this function has two roots, one here and one here, then by Rolle's theorem, we get a contradiction, right? Rolle's theorem says there must exist a place where the derivative is 0. And actually this says something kind of deep about, what do we know about this function? If its derivative is always positive, then loosely speaking, what can we say about this function?
Always increasing.
It's always increasing. And if a function is growing and growing and growing all the time, it can't cross the, that's like a monkey which is just on escape velocity out of the solar system. He is never coming back.